And we don't. Right? We don't have any. Right?
Oops, what happened? And the second half of the semester, I have modified grading. Just no exams 2 and 3. Homework, I'm waiting more heavily than I would otherwise. And then the project is worth 42% and participation will be worth 10.5%. So just a couple of reminders as far as deadlines. Just to remind you that we do have just checking to make sure that I'm still recording. Sorry about that. Let me just check. We're good. We do have homework due today. You've got homework for greenhouse gases, and you've got homework on air pollution regs. And the homework on air pollution regs shouldn't take you very long to do. It's pretty much all multiple choice. Also, a reminder that the semester project is posted on LonCappa. There's a folder called Semester Project that includes details of the project, team assignments. You should have connected with your team members. If for some reason you have separately formed a team different than what's up there, please contact me, preferably today, so that I know what's happening and that we can adjust team assignments. The interim report is the first thing that's due on April 6th. So take a look at that. If you have any questions, maybe what we'll do is we'll spend a little bit of time on Friday. Hopefully you've had a chance to look at it. And then if anybody has any questions, I can address those. So let's move back to the lecture. And we left off, we had looked at atmospheric stability. Now, what I want you to do with this is remember that what you're always doing is you're comparing the dry adiabatic lapse rate or the wet adiabatic lapse rate to the environmental lapse rate. So if we look back at this, this states absolute stability. So what we have is we have an environmental lapse rate, so the environmental temperature, so we can determine the lapse rate. We have the dry, the dry adiabatic lapse rate here. And then we have cloud formation right here at 2,000 meters. And then we have a moist adiabatic lapse rate. And sometimes it doesn't seem to want to work. Lapse rate up here. And that's not what I wanted to do. Okay, let's go back here. lapse rate. So what you're doing is you're always comparing the dry adiabatic lapse rate to the wet or the moist adiabatic lapse rate. So think of this as your balloon or your parcel of air. In this case, the parcel of air, the temperature of the parcel of air is less than that of the environmental lapse rate, so that parcel wants to sink. Same thing here. Here's my parcel of air. We compare those two. It is always less than, so my parcel of air wants to sink. So both below clouds formation and above cloud formation, that parcel is going to sink. Now we look at absolute instability. Again, we have cloud formation here. What you see here, you can see these puffy clouds. That's what you'd expect under these temperature or conditions. We have, again, the environmental temperature here. So we have an environmental lapse rate. And it doesn't want to work. Lapse rate. Okay. And then we have, in this case, we have the dry adiabatic lapse rate below cloud formation and the moist adiabatic lapse rate above. Again, compare these. Here's my parcel. So my parcel of air always corresponds to that adiabatic lapse rate. So now temperature is greater. So what does it want to do? It wants to rise. Same thing here. Here's my parcel of air, and it wants to rise. Okay. Now what I want you to do, and I'm going to have you take a look at this. Somebody can maybe chat. I know we can't have you work in groups, but what I want you to do is take a look at this. Okay. Now we have conditional instability. Just take a couple minutes, look at this, and see if you can convince yourself that where we have conditional instability. Okay, so what does that mean? Okay, so I'm going to let you take a look at that just for a minute or two. Minutes or two seem even longer here. Okay, so let's take a look again here. Now let's look. The purple line is the environmental lapse rate. So again, here is my temperature, so I can take that, and that's what I'm using to determine this environmental lapse rate. So that's the purple line. Here, let's put a parcel of air right here. So what do we see? That parcel of air, temperature of that parcel of air is less than that of the environmental lapse rate. So what does it want to do? It wants to sink. So if it wants to sink, then it's stable. And let's continue. Now, because we have cloud formation, the temperature of my parcel is still less, but I'm going to use that moist adiabatic or the wet adiabatic lapse rate. So again, I'm comparing those two. It's still less, so it wants to sink. At this point right here, the temperature of my parcel and the temperature of my environment is the same. So essentially at that point, it would just want to, that balloon would just want to sit there. Now, here, let's look up here. It's a little easier to see it if I go higher up. Okay, now what happens? Now the temperature of my parcel is greater than that of the surrounding. So you can see it's greater than that. So what does it want to do? It wants to rise, and now we have unstable conditions. So this is referred to as conditional instability. We can also talk about neutral stability, in which, in this case, and I still sometimes do not understand why this doesn't work, but the environmental lapse rate is equal to the dry adiabatic lapse rate. If the air is saturated, so if we have cloud formation, then you're going to use the moist adiabatic lapse rate. If you don't, below cloud formation, you're going to use the dry. Okay. And at this point, if you have neutral stability, then the parcel doesn't want to rise or sink. It's just going to essentially it would kind of stay there if it could. Now, we also talk about a super adiabatic lapse rate and a sub adiabatic lapse rate. So let's just draw a diagram. So we've got temperature and we've got elevation. And I'm going to change the color. So what we have is, let's draw the dry adiabatic lapse rate. Okay. Now, if we have a condition here, so let's draw this one. Okay. So this is my environmental lapse rate. My environmental lapse rate is greater than my dry adiabatic lapse rate. So what does this mean? My parcel wants to rise and it's unstable. Okay, so this would be a super adiabatic lapse rate. If I have a condition here, sorry. Trying to get. Why is it not erasing this? I apologize. You can laugh at me. I don't know what I'm doing. And there we go. Now we can get rid of the eraser. Or go back to this one. Okay. And wait, there we go. It still doesn't want to draw. Okay, so this is our sub-adiabatic lapse rate. In this case here, so this would be sub, and there we go. Okay, so now under this conditions, my parcel wants to sink. So this is a super adiabatic lapse rate here. This is a sub-adiabatic lapse rate. The last one we can draw is, again, we have a dry adiabatic lapse rate. In this case, what we have is we have a plot that looks like this for our environmental lapse rate, and this would be a temperature inversion. Okay. Does that make sense? Any questions? Okay, what we now want to do is we want to move on to looking at what we refer to as mixing depth. So in this case here, okay, what we have a plot, again, we have Z. And we have temperature. Okay, and what we see is, again, we have this unstable. So we have a super adiabatic lapse rate. We have a stable condition here. We have a sub-adiabatic lapse rate here. And then here, the environmental lapse rate. So this is our environmental lapse rate. And our dry adiabatic lapse rates, those lines are parallel, so we have neutral conditions. What we're typically doing, okay, when we're looking at determining mixing depth, we're going to use this, what we refer to as Tmax, and I don't know why this is writing on this slide, but Tmax is defined as the average maximum surface temperature for that particular month. So if we were to look at March, what we would do, that Tmax that we would use would be the average maximum surface temperature for the month of March in East Lansing. We're going to draw the dry adiabatic lapse rate from this. We're assuming in this case we don't have cloud formation. And where this dry adiabatic lapse rate intersects with our environmental lapse rate, that distance is the maximum mixing depth. So we'll draw it from the surface. This Tmax is the average maximum temperature for that particular month. So let's look at a problem. Okay, so we have a situation here. It's sunrise, the air is motionless, and we have a ground-based inversion. The ground level temperature is 10 degrees C, and the temperature of the air is increasing with altitude at a rate of 0.1 degrees C per meter. And it's to an altitude of 120 meters. At 120 meters, the lapse rate is now minus 10 degrees C per kilometer. So it's going to decrease at minus 10 degrees per kilometer. We have smoke emitting from a wood burning stove, and it leaves a chimney at a height of 1 meter. And we're going to assume that it has negligible velocity. And this is going to rise at my dry adiabatic lapse rate. So this is essentially, think of this as the parcel of air. And what you want to do is determine the mixing height of the smoke. So let's just work through this. So we have a ground temperature of 10 degrees C. The air temperature is increasing with altitude at a rate of 0.1 degree C per meter to 120 meters. And at that point, then it starts to decrease. So the temperature is decreasing at minus 10 degrees C per kilometer. Okay, so let's just draw this. What do we have? So we have Z, and we have temperature. Okay, at 10 and 20. Okay, and let's mark this at 100 meters. So what's going to happen? This is going to decrease, and it's decreasing at 0.1 degrees per meter. So at 120 meters, that temperature has decreased 12 degrees C. So, or sorry, has increased 12 degrees C, sorry. So we're at, this would be 22. So it's going to increase here, it should be a straight line. And this is at 22 degrees. It is 120 meters. So that's my environmental lapse rate. And then it's going to decrease. So if we go up to 200, 220. Okay, now it's going to decrease at 10 degrees per kilometer. So that's 1 degree. So if it decreases 10 degrees per kilometer, that's 1 degree per 100 meters. And it's going to decrease. We have it here. Okay. Now we have a chimney right here at 20. This is going to decrease at 10 degrees. So it's dry adiabatic per kilometer. And this is then going to be, and did I do this? So it's 10 degrees per kilometer, so that's 1 degree C per 100 meters. So we'll draw this, it's 1 degree per 100 meters, and we should have a line that looks kind of like, okay. So this is our dry adiabatic lapse rate. This is our environmental lapse rate. Where these two cross is our mixing height. So TZ, the smoke, is equal to 20, that's what we start with, minus 10 degrees C per kilometer, or we can divide by 1,000 meters per kilometer so that we have it in meters. Z minus 5, because we actually start at 5 meters above, and TZ for the environmental lapse rate is equal to 10 plus, because the temperature is increasing, 0.1 degrees C per meter times Z. We're going to set TZ smoke equal to TZ environmental lapse rate. And we can solve for Z. And when we solve for Z, the mix, so this is our mixing height. What's going to happen is at this point here, parcel rises to here, and then we're not going to get much mixing beyond that. So this is our plume. And that's what we're trying to ultimately get to the point of being able to predict where or how this pollutant is going to move in the environment. Questions? This makes sense? We're going to need this concept when we start looking at modeling, because what we'll need is we'll often need to be able to determine what is the mixing height. We're going to use the concepts of stability, unstable in atmospheres, mixing height, and we'll use that to be able to determine whether or not the pollutant is dispersing and what the concentration is downwind. We want to be able to assess whether we have a situation that is potentially dangerous, harmful to the environment and public health. And the other concept that we look at is ventilation coefficient. And this is the maximum mixing times the average wind speed. And we'll go through a calculation with this. And what it really is, this is a way of assessing whether or not a pollutant is going to disperse out into the environment. So if we have a smokestack here and we have a pollutant, what we want to know is that pollutant going to disperse? Or, for instance, are we going to have a condition that ends up drawing that pollutant down and down to the earth, and this poor person down there is coughing because of the pollutant. If the ventilation coefficient is less than 6,000 square meters per second, that considers to be a high potential. That means, that's kind of this condition right here. You've got a condition where that pollutant is likely to not disperse, is much more likely to end up close to the surface of the earth, close to where people are, and potentially will cause health impacts. So in order to do that, what we need to do is we need to be able to calculate the wind speed at various different elevations. I changed this slide slightly from what I had posted earlier. Basically same information, but I just reordered it. U sub A is the wind speed at the height of the anemometer. So the anemometer is what we're using. If you go on weather.com or some other weather site, and it tells you what the wind speed is, that is measured typically at 10 meters above the surface of the earth, wherever you are. So we're going to call that Z sub A, as the height is typically, it's going to be 10 meters. So this here is typically 10. We want to be able to determine the wind speed at some height other than that of the anemometer. It may be the height of a stack. It could be at the mixing height, but it's some other height other than that of the anemometer. And then P is going to be and this is P right here, is a dimensionless parameter that varies with atmospheric stability. And this is a table of these wind profile exponents, P. This is for rough terrain. The rougher the terrain, the more the wind speed will vary from that which you measure at the anemometer. So if you increase roughness, that increases P. If you have a smooth terrain, I don't know, maybe you're out in a cornfield in Iowa, Illinois, and you have very smooth terrain, then you're going to multiply this exponent here. So you multiply this by 0.6 for smooth terrain. Okay, and you'll need to think about this, and you'll use this table again. We'll talk about it again when we talk about modeling, because we will use this extensively in determining wind speeds, and there we'll look at wind speeds predominantly at the stack height, although it could be at the mixing height, depending on the model we're using. So let's look at a situation where we have an atmospheric profile that's isothermal. What does that mean? That means, again, we have Z, we have temperature, it's isothermal at 20 degrees C, so the temperature doesn't change with elevation. The estimated maximum daily surface temperature, this T max, don't ask me. Okay, so we'll try this again. Okay, so this is 20 degrees. T max is 25. The weather station, so Z sub A, is at a height of 10 meters above the elevation of the city, and we have rough terrain. And the average wind speed that's measured is 3 meters per second. Okay, so that's the situation we have. And what we want to be able to do is we want to estimate both the mixing depth and the ventilation coefficient. And I've told you that what we have is we have moderately unstable conditions. So let's go back to this. We have moderately unstable conditions here. So my exponent is 0.15. I have rough terrain, so I can use that value. So P is equal to 0.15. So let's go and so we have T max equals 25 degrees. Here we have isothermal conditions at 20 degrees C. So let's look at this plot. We have 20, let's draw this, we have isothermal, and we have 25. So let's draw this for 500. This is 1,000 meters. Okay. So we're going to use the dry adiabatic lapse rate for this line right here. Okay, so we're dry adiabatic lapse rate is equal to minus 10 degrees C. And don't ask me what I just did there. That's what I did. I apologize. And somehow I moved this over, but I'm going to leave this here because okay, so we have a dry adiabatic lapse rate of 10 degrees per bear with me. I apologize. I'm not quite sure what has happened here. There we go. Now we're back. Okay. 10 degrees per kilometer. So at 1,000 meters, we would have a temperature of 15 degrees. And I haven't drawn this very well, but it gives you the sense, okay? So this is our isotemperature line. This is our environmental lapse rate. And then we have a dry adiabatic lapse rate. So let's just think about this. In this case, here is our parcel. Our parcel has a temperature greater than that of the environmental temperature. So what does it want to do? It's going to rise. So what do we have? We have an unstable condition at this point here. Crosses this line. Now it's my parcel temperature is less than. And what happens? Now it wants to sink. So we have a stable condition here. Okay. What we want to do is we want to determine this temperature. I'm just going to use the surface temperature here. And we have T TZ, dry adiabatic lapse rate, equal to 25 minus 10 over 1,000. This is 10 degrees C per kilometer. And this is 1,000 meters per kilometer. And I'm going to multiply that by Z. TZ, environmental lapse rate, is equal to 20 degrees C. And where those two are equal, that will give us the mixing height. And the mixing height is 500 meters. Now, typically, okay, your question was, how did I get the dry adiabatic lapse rate? This is given. So that's something that is given if your dry adiabatic lapse rate is independent of elevation and it's independent of temperature, and it's always around 10, minus 10 degrees C. I think the coding, and I have in your homework, when you do the homework, I think I have it coded as minus 9.8. It's a little more accurate, but I have that in the coding in terms of what to use for the dry adiabatic lapse rate. And I apologize for my lack of experience with the tablet. I guess by the end I'll get used to it. Okay, so this U, U is equal to function of Z. Okay, so it's going to change as with elevation. What we're going to do is we're going to determine U at 1/2 of the mixing height. Okay. Because above that point, U is going to be less than whatever we determine at 1/2, and above that is greater. So it kind of gives us an average U. So U2 over 3.0 is equal to 250, because we calculated. So 1/2 of the mixing height is 250 meters, divided by 10, which is the height of the anemometer. We're going to multiply that by 0.15. We said that P was equal to 0.15 for rough surface. And if we solve that, we end up with U2 is equal to 4.86 meters per second. Okay. So the ventilation coefficient is equal to this 4.86 meters per second times the mixing height. So we end up with meters squared per second. And that is 2430 meters squared per second. We're going to compare that to the 6,000 that we mentioned earlier. It's less than that. So what does that tell us? Okay, this here is less than that 6,000. So what do we have? We have that situation here. Here's our stack. Here's our chemical plume. And this plume is not going to disperse very well. And we're going to end up with a condition here where there is the potential impact on human health and the environment. So that is a condition that would be considered potentially hazardous to health. Okay. The last thing we want to look at are some of these different types of plumes. So what do we have here? And I'm going to try and see if I can make this work. Okay, so let's look here. In this case, this line here. So I've tried to draw the red line as That's the adiabatic lapse rate. So this, let's just take this as a dry adiabatic lapse rate. So what do we see? Okay. In this case, what's going to happen to that plume? Here's our parcel. Okay. What we have here for looping is a super adiabatic lapse rate. And what do we have? We have an unstable condition. What does it want to do? It wants to rise. And typically what you get is you kind of get this looping plume. Okay, so if you see that, you have unstable conditions, super adiabatic lapse rate. It's greater than the environmental lapse rate. A coning, now here, this red again, is our dry adiabatic lapse rate. Now what's happened, okay, this is less than the environmental lapse rate, and what does it want to do? It wants to sink. So we have a weak lapse rate, and there you tend to have what they refer to as a coning. So you'll get some of it rising, but it'll cone out more like this. A fanning means we have an inversion. And in this case, the plume is just kind of fanning out and it's not dispersing. It's going to fan. So we get potentially a horizontal dispersion, but we don't get much vertical dispersion. Lofting here, you've got a situation where now the release of the pollutants is above the inversion. So think about it here. If so what happens here is you don't get much movement vertically down, but you get this rising upward. So you have this lofting plume that looks like this. In this case, fumigation is the worst. Here, your smokestack is below this inversion layer. And what happens is now you don't get much movement upwards, but what's going to happen? It's going to all move downwards. And then potentially you've got a situation that is highly detrimental to human health. And trapping, again, you've got this version. Loft, you get a little bit more dispersion vertically than you do with fanning. Okay, but essentially it's just kind of moving, and you're going to get more. Basically, this is just going to move downwind, and you're going to not get a whole lot of dispersion this way. So these are just the types of plumes that you can see. Fumigation, like I said, is basically the worst. This is the worst case scenario where you've got a smokestack here, and basically you don't get much dispersion, but then that all that pollutant just stays below the mixing layer, and now you've got a lot of people that are coughing and become sick because of the pollutants. So any questions about what we talked about today? I'm not going to start modeling. We'll start modeling on Friday. Any questions, comments? Just a reminder then, you have homework due tonight, and I have posted information on the semester project. And a reminder that the interim report is due April 6th. You should have connected, or should connect very soon with your team members. And if you've formed a team that is not the same as what's posted on LonCappa, please let me know ASAP so that I can respond. Any other questions? I apologize for my challenges dealing with the tablet. I'll get used to it eventually. And I will then end this, and I will either see you at office hours, if anybody, I'll be in office hours, so I'll be on Zoom for that. And otherwise, I will see you on Friday. Take care. And again, see you on Friday.